All right, for question 7, it says to compute each iterated integral by reversing the order of integration. Okay, so for part A, we're looking at the integral of the function y times the sine of x squared. And the order of integration here is dx dy, and x varies from y squared to 9, and y varies from 0 to 3. Okay, so first off, if you were to just blindly attempt to integrate this thing as it stands in this order dx dy, since for the x integral you're holding y constant, you're going to have to integrate the sine of x squared, and no matter how hard you try, you're going to run into a wall. Okay, it's actually been proven that there's no elementary antiderivative to the sine of x squared, and so that's going to be a fundamental stumbling block. So if we're going to have any hope of evaluating this thing, we're going to have to reverse the order of integration. So what I want to do is write this as an integral in the order dy dx. And so now what I need to do is just find these bounds. And as I pointed out before, since we're not integrating over a rectangle, okay, it's not as simple as what we saw with Fubini's theorem, where we just reverse the order and then just swap the limits of integration, right? Now we have to be very, very careful with regards to how the limits correspond to our region of integration. Okay, so let's go ahead now and describe that region. So for x, right, we're saying that x ranges from a low end of y squared to a high end of 9, and then y ranges from a low end of 0 to a low end of 3. Okay, so what does this region being described with these inequalities look like? Well, let's just start with x, right? If x was y squared, that looks like this parabola on its side. Okay, and if x were 9, well, that's going to be a vertical line here, just at x equals 9. So let's say 9 is right here. Okay, and so then up here, this is x equals y squared. And since our order of integration is dx dy to start, right, this says, well, first we're going to fix a y. So we'll fix, say, a y up here. And y is taking on values from 0 to 3. And then what we're going to do is we're going to let x vary from y squared. So the low end here for x is y squared, which is this point along our parabola. And then we're going to go out to the high end when x is 9. Okay. So our horizontal strip will run from, again, y squared there to 9 there. Okay. And notice we're letting y vary from 0 to 3, and this point here, when x is 9, if x is 9, then y, taking the square root of 9, would be 3. So we see that y goes from 0 to 3. So you put all that together, what we're doing is we're stacking these horizontal strips now as we let y vary from 0 to 3, and that's going to fill out this region right here. It's bounded by our sideways parabola, the x-axis, and this vertical line x equals 9. Okay, great. Well, so now to switch the order, okay, we're going to now fix an x first. All right, so think about now fixing an x. And now we're going to let y vary. And so we're going to let y vary from the low end here, which is just on the x-axis, up to this high end when we're on this sideways parabola, right? So the bounds here now would be y equals 0 up to y is equal to what? Well, since we're on the parabola and we know the equation relating x and y is right here, x equals y squared, if I solve this for y, we'll get that y is the square root of x. Okay, so for the y bounds, those are going to be from the from 0 to the square root of x, and then we're letting x vary from is 0 to 9. Okay, great. So does this help? Well, hopefully. Let's integrate now with respect to y. And as we can see, since x is held constant, we can compute this integral, right? That would just be y squared over 2 times the sine of x squared. And we're going to evaluate that from 0 to the square root of x. And then we have our dx. All right. Now we'll go ahead and factor that 1/2 out in front. And when I plug in square root of x in for y, I'm squaring, so I'm just going to get an x. And then I have my sine of x squared. And then if I plug 0 in for y, I'm going to get 0, and so that's it. Okay, so now this is looking a lot better. Now this integral I have here, while maybe not the easiest integral, it is definitely computable, because the thing to notice is that inside the sine I have an x squared. And the derivative of x squared is 2x, and I have an x out front, so the idea here is use a substitution. I could set u equal to x squared. So du would be 2x dx, okay, or put it another way, x dx would be du over 2. Alright, so then to write down the integral, we're going to have 1/2 times the integral of, so I'll put the sine of x squared part first, that's just going to be the sine of u, and then for the x dx part, that is du over 2. And then lastly, I'm going to go ahead and change the limits of integration. And so to do that, let's go ahead and say, well, if x is 0, then u would be the square of that, so be 0. And if x were 9, then u would be the square of 9, so that'd be 81. All right. All right, so this is definitely better, right? Maybe not the easiest thing in the world, but definitely better than what it was. So I'll bring this half out front, so we'll get 1/4. And now we're integrating sines, so that's going to give us minus cosine. And we're evaluating from 0 to 81. Okay, and so now go ahead and plug in 81, and you're going to get the cosine of 81, which is just cosine of 81. There's nothing really further you can do with that. And then minus the cosine of 0, and that's just 1. Okay, and so this is a perfectly fine way to leave the answer. However, aesthetically, some people don't like a leading negative like that, so you can bring that in and say 1 minus the cosine of 81. Okay, so that's going to do it for this one. We'll look at part B in the next video. Thanks.